In this video, we want to address the issues of fitting polynomials with higher orders in Python, and we also want to look at numerical differentiation and integration. Okay, and to start, let's assume that I have some data, and this data looks like this, okay? And so this is just some generic XY data, and this could be positions and times, or positions, velocities, etc., whatever, or times and velocities, whatever the case may be. For the moment, let's assume that they are times and positions. So I would label this as my time column. This is my position column. And it looks like we've taken measurements every 0.1 seconds, right? So we have some sort of stopwatch that we're taking measurements of. And we have a ruler that we're taking position measurements with. Okay. So first things first, what we first want to do is look at what this data would look like when graphed. Okay, and so this clearly looks like a polynomial. If I select the add trend line, it doesn't even let me choose exponential because of this 0, 0 term or set of data points. And same thing with the power. But if I click through, and it won't let me do the logarithm either. So with that being the case, the polynomial is definitely a better fit than the linear, right? Now, of course, you can choose higher order terms and always get better fits, but at some point, unless you have a good physical reason to do so, it's rather pointless and cumbersome. Okay, so typically, if you need to fit with anything higher than a linear, you want to judiciously choose your order of your polynomial. Hopefully you have a theoretical reason, such as positions and times under constant acceleration that is predicted to be a polynomial, a second order polynomial, a parabola, or you have some mathematical or graphical reason. So if you're trying to fit some feature in a data set and remove it, and you don't care what the cause of the feature is, you just want to remove it, and you choose some order of polynomial to try and fit the data and subtract it out or divide it out. But don't make work harder on yourself, right? Okay, so first things first, we can clearly see what the results of the second order fit are. And so we have our coefficients, 9.6061, 0.7594, and 0.0685. Now we're not going to calculate the R² value for higher order fits in Python, all right? But we will do the polynomial fit to get the coefficients for this parabola, okay? So how do we do that? So if we come in here, and I've already got the data loaded, and if you want to double check just to make sure that the data matches, we can plot And if I run this, it should plot, and my plot should look like the untrend valued version. If I delete the trend line, our plot should look very similar, and it does. So we're pretty confident that this is, we've typed in our data correctly. And now, so how do I get the trend line? Well, first things first, I'm going to undo the plot. And what we want to do is the same thing we did before when we were using the polyfit routine to fit the data with linear trends. So what we can do is say, I want to call the polyfit function, and again I've imported my libraries, numpy as np and matplotlib.pyplot as plt, and I want to fit this data set x and y with a second order polynomial. Okay, and just to convince ourselves that this is the syntax, we can run it as is, and it doesn't complain at us. So since it doesn't complain, we're okay. And so now what I can do is I can say, I can do a variety of things. Okay, I can tell it to print z, and this will print the coefficients in order. So here we have 9.5946, etc. And something is a little weird. That's because that should be a 10. There we go. I had mistyped one of the data points. So here we go, 9.606 and 9.606, 0.7594, 0.75939, so that gets rounded up to a 4, and 0.0685, 0.0685. So this gives you the coefficients. Now, if I want to bind these coefficients to specific variables, remember what we can do. If we want to build a model, what we can do is say, okay, the model is saying take your first coefficient and make that your quadratic term. So I'm going to say z0, the 0th element of my z array, multiply that by x squared plus z1, or the second element of my z array, and that's going to be my linear term. And then the last one is going to be the intercept. So the way the polyfit function works, no matter what your order is, your first term in your array will always be your highest order term, and then it'll just descend from there. So if I made this a 6th order fit, I would have 7 coefficients, a 6th order, a 5th order, 4th order, 3rd order, 2nd order, and 1st order, and then I would have the constant intercept. Okay, so whatever number this is that you're fitting, you'll always have one more parameter than that, right? So whoops, and this needs to be z2. Okay, so once again, let's make sure that it doesn't complain at us. And so now what I can do is say, okay, I want to plot my x and y data. I'm going to print black dots, and I want to plot the model on top, and we'll give it a red double dash. And now this should mirror the trend line given by Excel, and sure enough, it does. Okay, so this is the easy way to fit data with trend lines. Okay, so it doesn't matter what order you need. You can specify this up to, I don't know if there's a maximum order, but of course there's a practical limit, right? Unless you have a really good reason to. I don't see why anybody would need to go above order 6. Unless you had a really good reason. But that's how you do it. Okay? Now, one of the things we know, if this is times and positions, okay, if these are times and positions, one of the things that, one of the things that we're going to be interested in is taking a numerical derivative, right? So how would I take a numerical derivative of this data? One of the simplest methods, okay, and in fact, let me actually take a screenshot of this, and let me open up Paint. This will be easy to do. So a way to take a derivative, okay, remember that a derivative is equivalent to the slope through a point. So if I want to calculate the slope, for example, through that point, I want the slope through that point that's tangent to the curve. Well, we won't be able to get this perfectly, right? This will not be perfect, but we can get a good approximation. So how do we do it? Well, one of the simplest ways is to find the difference in the y positions. I won't try to type that out. That'll take too long. But just note that this is, if this is your y position, okay, if this is your y sub I position, okay, then this would be your y I plus 1, and this would be your y I minus 1. And this would also be your xi, so this is xi, yi. And so this point here would be xi plus 1, yi plus 1. And this would be xi minus 1 and yi minus 1. Okay, so if you take the slope, if you find the slope through these points, you will get a good estimate of the slope through this point. Okay, so this is called the central difference method. This is called the central difference method, where you take the difference between the neighboring points in y position to get the rise, and then take the difference in the neighboring points in the x position, and that gives you the run, and then the slope is the rise over the run. Okay, so that is the motivation here. Okay, now how do we apply this? Okay, so the way that we're going to apply this is we're going to have to, this is the place where we're going to introduce what we call loops. Okay, and it'll probably be best illustrated if we do it in Excel first. So let's do this numerical derivative, or y prime, in Excel first. So the whole idea is to take a data point and take the corresponding y value and subtract the previous y value, but there's no previous y value here. So I can't use the first data point. I have to start with the second data point. Okay? And so what I'm going to do, take the difference in the y values surrounding the point I'm interested in, and then take the difference in the x values surrounding the point that I'm interested in. So that gives me the approximation of the derivative, or the slope, through this first point. Okay? It's approximately 3. If we're in meters and seconds, then this would be approximately 3 meters per second. My velocity at this point would be approximately 3 meters per second. And then what I would do in Excel, I can just easily click and drag this down. And so what that does is this formula then approximates the slope automatically, and it works through each point. And you'll notice that these cells are updating as I click through the data points. And just to make sure, we're in the 6th row. So this should be D7 minus D5, and that's what it is, divided by C7 divided by, minus C5. And that's what this is. So this is what we call an iterative process. Okay, this is an iterative process. I do something once, but then I want to continue doing that same thing for my entire set of data until I can't do it anymore. Okay, so this is what we call iteration, or iterative process. Okay, and there's another definition of iteration where you would do a process on a set of data over and over and over again, but that's a little bit more advanced. But for our purposes, we just need to run this algorithm through our loop one time. Okay, so what I've done is I've created a new column for numbers. So what that effectively means in Python is, and I'm going to backspace all of this. What that effectively means is I need to create a new array, and there's a few different ways you can do it, but for starters, okay, note that I don't have anything here and I don't have anything here. So this array is going to be, it's going to have 2 fewer elements than either my positions or times. Okay, it's going to have 2 fewer elements than either my positions or times. There are a few ways that you can go about this. For now, we'll just do it this way. There's 10 elements in each, so I'll just create an array of 8 zeros. And is that 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoops, overshot it. Okay, so there's our element of 8 zeros. And what I'm going to do is I'm going to do what we call a for loop. And this syntax is going to require just a little bit of explaining. Okay, so here's the first line of my for loop. So this is going to say for, and I is now an index. So I is going to be the index. And again, remember that the index goes from 0 to 1 and then up through your measurements. And so what we're saying is we want to start, okay? We want to start with the first index, all right? So how would I do that? There's multiple ways I can go about this, but going back to the first line, so this I is going to be your index, and so this is basically saying for I in the range, the length of z. Okay, so what we're telling Python to do is we're telling Python to look at each individual index starting at 0 and telling it to then do something this number of times. This is the length of z, which is 8 elements. Okay, so we're going to tell Python to look at these numbers and tell it to do a calculation 8 times. And then we're going to update the elements of z as we go along. And when you have this first line of your for loop written, okay, so your range needs to be in parentheses, right? So however many elements you want to, or however many times you want to execute the code, the algorithm in the loop, that number needs to be here. But we know that this number is 8, but it will often be advantageous to define it by the length of one of the arrays, because you won't often know exactly how long those arrays are. Okay, you may be working with really, really big data sets. So it's my personal preference just to go ahead and start this like this, right? And then you have a colon. And the colon is essential. Your code will not work if you have a colon. Now, Python recognizes loops by ending the first statement in the loop with a colon, and then when you hit enter, all of the subsequent text will be indented until you manually unindent. Okay? So this is where the loop is going to get executed. So here's what we're going to do. We say for I in range len z, and I is going to start at 0. So I can't start the calculation at 0. I have to start the calculation at 1. So what I'm going to say is z of I, right? Z of I. So I is going to start at 0, and this is z of 0. This is the 0th element of I, is going to equal the difference between my subsequent y value, but this is going to be y plus 2. Or I'm sorry, I plus 2, because I is starting at 0. Python is starting the index at 0, but I need this y element, okay, because this would be yi1, and this is the first element in the z calculation that we're going to do. So I need to choose yi plus 2, and I need to subtract yi. And this is going to take, Python's going to say, okay, I'm looking at index 0, so I add 2 to the index and go to that y value, and then I'm going to subtract 2, or I'm going to go back to I, essentially, look at that y value, and take the difference between them. And so, okay, and then I'm going to divide that by the x values. Okay, so let's just make sure that Python's not complaining at us for some reason. And it's not, okay? So now what we can do is, let's say, so notice I had to manually back out. So as long as you are in the loop, it will stay indenting until you manually backspace. Okay, so you have to manually backspace out. And now if I print z, I should get the same results that are in my table in Excel. So 3.1, 4.566, there is something wrong. Do 3.1 is good, but not 5.8. 0.62, 1.37. What is wrong here? I'm not seeing it off the top of my head. So I'm going to pause and then we'll come back and I'll let you guys know what I find. All right, I found it. I need to replace these with i's. The subtracting the 0th index works for the first calculation, but not the subsequent ones. Because when I here is going to equal 1, we're in the second index here, and so that's going to take the 4th index and subtract the second one, and divide that by the 4th index in the x array and subtract the second one. Okay, so I had just accidentally replaced the i's with zeros. And now our numbers match. 3.1, 5.8, 6.85, 6.55, 10.55, 11.75, 13.5, and 18.25. So we have now taken a numerical derivative, okay? So once again, this loop is basically working through each index value and doing something with the elements according to the rules that you put into here. Okay. So that is how you would do that. Now, if you don't want to just keep typing out zeros here, there's a few different ways you can do things, right? One way is, instead of using an array, you can use a list. And so a list, remember, is just slightly less algebraic. You can still do things with individual list elements, but you can't do all of the vector mathematics that you can with arrays, like summing them up and multiplying them by each other and things like that. But what you can do is you can define a list with 0 elements to be the length of your X array minus 2 elements. And again, that's because we have to drop the first element and the last element, so we're actually getting the total length of our X and Y arrays minus 2, because we're dropping the first and the last. So that's where the minus 2 would come from. And this now should still work exactly the same. Okay. So this is basically a shorter syntax for writing out that whole string of zeros. Okay. Now you'll notice that the values are a little bit different, right, due to rounding errors and so forth, but the values are all the same, and they're all equivalent to well within 0.0000001%. And for our purposes, that's going to be perfectly fine. Okay, so that's another way you can do it. And this actually, I believe this syntax would do it too. So let me put a line in here. So I'm going to have it print z twice. np.zeros makes an array of zeros, just like I did typing it out manually, but defines the number of zeros in the list this way. I believe this syntax should work. Okay, yes, and sure enough it did. So the first thing it printed is an array of 8 zeros in floating point, and then it did the calculations and obtained the correct values for our numerical differentiation. Okay, so that is how you can numerically differentiate data. Okay, and if I wanted to be very clever, I could actually, before we do that, we would have to if I want to plot the x or my z data, my derivative data, with my corresponding x values, what I could say, I can create a new x list, call it x new, and I can simply copy and paste these array values in there, because these are the ones that the calculation uses, and I can plot this data actually, I just want to show that. And this would give me the numerical derivative, right? And you can see that that's roughly linear. And the outlying data point here is due to slight inaccuracies in the original data, and same thing with this outlying data point up here. But by and large, I can draw a trend line straight through here, and I can even do that. So let's define a new function, and let's call it P for polyfit. X new, Z first order, and model is going to equal P 0 times X new plus P1 and let's make it a red solid line, and this should draw a linear line through the data, and I need to NP. Right? So if I wanted to know the slope of that line, I could tell it to print P0. And if I just tell it to print P, it'll print both things off. And so the slope is 19.4, which would be the acceleration. And the intercept is 0.79. So if we come back here, we see that this actually kind of agrees, because remember that if this is an accelerating object, that the coefficient on your parabola is half of your acceleration. And so we would predict from this data that our acceleration was right around 19.2, and here we're measuring 19.4. So both sets of data give decent agreement. It's not tremendous agreement, but it's decent agreement. Okay. So that is numerical differentiation. There are more sophisticated ways of doing this. Okay. Especially if you have really, really large data sets. But to prove to you that this works on actual functions, okay? So let's prove that this actually works in real functions. Let's let x equal Okay, I'm going to create an array of x values from 0 to 10 with 1001 data points. And I'm going to create a function out of this. And I'm just going to use the sine function, because we know what the derivative of the sine function is. Right? We know what the derivative of the sine function is. The derivative of the sine function is, of course, cosine. So if I plot this, right, we should get a really solid sine curve. Even though these are individual data points, they're so close together they look like a solid curve. Okay, so let's do the same process that we just did. So first things first, let's define a new x list to correspond to our derivative list. Okay. Now, we have to do something unique here. There's several different ways you can go about this. Okay, there are several different ways you can go about this. But the first way is to just run this through a loop, okay, and say, okay, append the I plus 1 index value of your x values. So in other words, what we would be doing here, if I clear this out, and I'll delete my chart. So my x data is going to go from 0, 0.001, and so on. Okay, I'm not going to go through the whole 1,000 data points, but you'll get the idea of what I'm doing. X new, remember, is going to have to start here. So I want this to do this, right? But I need to neglect this point and my last data point. So these are my i's. Oop. And so on. So if I create a list of zeros with a length of 2 less than my x values, then I can start at 0 and tell Python to take I plus 1. And I'm going to do that for the number of elements in my x new list, which these are all zeros, remember. So what I can say is, for I in range, len x new. So I'm going to do this two fewer times than are in my x list, or I'm going to do it 999 times. I'm going to say x new I is going to equal x I plus 1. Because, remember now, this is the 0th index. This is the first index, second index, and so on. These are the indexes of my x new list, and these are the indexes of my x list. So my 0th index of my new list is going to equal the first index of my original list. And then I can do the derivative. And I'm going to do it 2 less times than are in my original x list. And I'm going to say I need to define a list or an array of my derivative values. And so zi is going to equal yi plus 2 minus yi. I'm going to divide that by xi plus 2, divide that by xi, and now I'm going to plot my derivative, and I should see a cosine curve. So I should see something that looks like that. Okay, I should see something that looks like that. Remember, when sine is at 0, cosine is either going to be at 1 or -1. And when sine is a maximum, cosine will be at 0. Right? So, that's what we should see. Right? And hopefully this works. Oh. This needs to be a minus sign. And there we go. And that is a cosine curve. Okay? So the algorithm is working properly. There are algorithms, and if you Google, okay, if you Google numerical differentiation, you will get all sorts of ways of doing it. The algorithm I'm showing you is not in any way, shape, or form the only way of doing things. Now, this particular reference, the Mathematical Python from personalmathubc.ca, this is actually from a textbook where the author put a lot of his work online. And he shows you how to do certain things, but this is much more advanced than any of the things I've shown you how to do. This involves definitions, which we will cover, but I have not shown you guys how to do that yet. But so this formula that he's using is actually the formula that we implemented. It takes the value of your function plus the next step up, and it subtracts the value of your function minus the next step down, and divided by twice your x interval, right? And that's exactly the formula that we did. I would say if you are interested, this reference is a very good reference to read. This is actually where I started to learn my own Python, and I highly recommend looking at that as a reference. But there are tons and tons of approximation methods, okay? There's not one that alone does or is quote unquote correct. Okay, there's not one that alone is correct. But I hope that you have found this helpful. The things to note are that we've introduced the concept of a loop. Now, the for loop is not the only way to do loops. Okay, so a for loop says the programmer has to specify the number of times the loop is in operation. Okay, you specify the number of times you want the loop to perform. There may be times when you don't know how often you want the loop to perform. You just know that you want the loop to perform a specific function until a specific value is obtained. And under those conditions, you would use what's known as a while loop. So a while loop says, I don't know how many times you need to operate. I just know the value of some parameter that I want you to calculate. And once you get close enough to that parameter, then you can stop. and that is how a while loop is implemented. Okay. Um, but so we've introduced the ideas of loops. We've shown you how to implement new arrays in numpy with the zero function. And we have shown you a basic algorithm to do numerical differentiation as well as higher order polynomial fitting in numpy, right? So this is a fairly dense video, but if you understand it and are willing to work through it, then this is kind of one of the steps into higher order computational thinking, the idea of the loops and the iterations. So I hope you have found this helpful, and in the next video we will cover numerical integration.